All right, my friends, we are on this last one. Again, we're reviewing that potato problem from last year's exam question, which I think was very good. I think it kind of hit on a lot of key stuff, and I don't know, I think it'd be kind of good for us to just go over this one more time, get practice. Now, part A, believe it or not, is 3 points, right? And I think, we are in business to make this work. So at time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in the kitchen. The internal temperature of the potato is 91 degrees Celsius at time t equals 0. So they're kind of giving us that kind of starting point, the starting temperature. And the internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. Cool. The internal temperature of the potato at time t can be modeled by the function h that satisfies the differential equation. So we're giving us the derivative equation where h of t is measured in degrees Celsius and h of 0 equals 91, which is pretty much what was stated right up above. Write an equation for the line tangent to the graph of h at t equals 0. Use the equation to approximate the internal temperature. So if we see equation to the line tangent, we know that's y minus y1 is equal to m x minus x1, but yet again we are in t's, so we'll do y minus y1 is equal to m t minus t1. Y is pretty much universal, so regardless if it's h, b, p, m, n, it doesn't matter. We can leave it as y minus y1. We do need to change the t's because our input needs to be expressed, and the problem it's t, we want to make sure it's t, and a regular old equation is always y equals, right? It's kind of generic, so that's why it's kind of nice to make sure you keep that into account. And the good news is we already know at t equals 0 the temperature is at 91, so this is y minus 91 is equal to m t minus 0. All we got to find is m. Well, we're already given this expression here. Well, usually we need to plug in 0, our x value, take the derivative, plug in our x value, and that'll give us a slope. Well, they don't give us the t anywhere here, and that's okay because we do know when t equals 0, h equals 91. So we just need to plug in 91 into there, so negative 1/4, 91 minus 27, and then we are in business. 91 minus 27 divided by negative 1/4. 91 minus 27 is 64. So we get negative 1/4, 64. 64 divided by 4 is 16, but the negative, so this is negative 16. So now we know this is, let me go ahead and scroll down here. Now I know, without a doubt, this is y minus 91 is equal to negative 16 t minus 0, okay? And that right there is going to give me alone 2 points. 1 point for this, 1 point for that. But it did say, use the equation to approximate the internal temperature at 3. So y minus 91 equals negative 16. 3 minus 0. 3 minus 0 is 3. 3 times negative 16. 3 times negative 16 is negative 48. So we get y minus 91 is negative 48 plus 91 to both sides. So y is equal to negative 48 plus 91 is 43, right? Degrees Celsius. Cool. So I think it's important for us to state. It's important for us to state, right, that the internal temperature, the approximate internal temperature of the potato at t equals 3 is 43 degrees Celsius. Very important for us to state that, right? We did the work, and I'll just write it down. Good. All right. Part B, well, we got to take the second derivative. Very similar to the problems we did before. We got to just distribute it across and do all that good stuff. But nonetheless, right? I personally think for now, let's go on to what matters most, which is this question down over here. I wrote the whole question down again, right? Problem 4, and then part C. I really just want to get to the nitty gritty, the parts that's going to give us our 5 points, right? Here, we've done this already multiple times on the previous video, and we'll do it at the very end, but I kind of want to emphasize how important it is to get this question right. because it's 5 points. All right. When t is less than 10, an alternate model for the internal temperature of the potato at time t minutes is the function g that satisfies the differential equation, where g of t is measured in degrees Celsius and g of 0 is 91. Very important that we remember this is your t, this is your g, right? Because we're talking about an alternate model. Find an expression for g of t. That means find the original. Based on this model, what's the internal temperature at time 3? So that lets us know right away. We got to take the antiderivative. We got to find the original. Well, we're given derivative. What do? Well, antiderivative, which pretty much means what? So that means, my friends, that we're going to have to do a little bit of work by separating the variables. dg over dt is equal to negative g minus 27 raised to the 2/3. Well, let's multiply dt to both sides. And let's divide by g minus 27 to the 2/3 to both sides. We just want to separate the variables correctly. All right, let's go ahead and go through. Let me just write this down maybe a little more nicely. 1 over g minus 27 raised to the 2/3 dg is equal to negative dt. Let's take the antiderivative now. Okay. Before I go to take the antiderivative, notice that I do have a power on the exponent of our denominator. So this can be rewritten now different than the ones we've done before as g minus 27 raised to the negative 2/3 dg is equal to the antiderivative of negative dt. This is really like a -1 if you want to think about it. It might be helpful to write that down if it helps. All right. Now that we got that there, my friends, let's go ahead and take the antiderivative. So this will be g minus 27. We're going to add 3 over 3 to both sides. So this becomes 1/3. And we're going to divide by that because it's the antiderivative. Good. Bam. What's the derivative of the inside? It's 1 because it's g, right? The dg matches 1. We divide by 1. We don't need to put that there. It's equal to, what's the antiderivative of -1? It's -1 times t plus c. Remember, this is dividing. The 3 can move up. So this is 3 g minus 27 to the 1/3 equal to negative t plus c. Now we're in business to go ahead and find our original function. We know, I'm just going to write it from the problem up above, that g of 0 equals 91, right? It's 91. Good. Let's plug in 0 for t, so we get negative 0 plus c. Plug in 91. 3, 91 minus 27 to the 1/3. This is equal to c. This is 3. 91 minus 27 is 64 to the 1/3. Now, if you don't know how to do this, don't do it. Leave it like that, right? If you absolutely have to, leave it like that, but don't give up. Keep working through. But really, remember, a fractional exponent means the cubic root of 64. What 3 numbers multiply by themselves to give you 64? Well, that would be 4. So this is 3 times 4, which is 12. So now we know my c value is 12. And now I can write it through and we'll finish this up. 3 g minus 27 to the 1/3 equal to negative t plus 12. There it is. And now we just need to solve for g, right? We need to solve for g. So let's divide everything by 3. Let's divide everything by 3 first. We get g minus 27 to the 1/3 is equal to negative t plus 12 to the 3rd. Let's raise both sides to the power of 3 over 1, which is, in other words, 3. Why 3 over 1? Well, 1/3 times 3 over 1, that's 3 over 3, right? 1 times 3, 3 times 1, which is 1. They cancel out. So we get g minus 27 is equal to negative t plus 12 divided by 3 raised to the 3rd power. Now the last step to do is add 27. And there it is. So we get, oops, g is equal to negative t plus 12 divided by 3 to the third power plus 27. And that is our initial condition. I mean, that is our OG function, g of t, right? So we're in business. So now we can write this to be g of t is equal to that. Now, be careful because this problem was actually a little sneaky. Find an expression for g of t. We did that. Now it says, based on this model, what is the internal temperature at time t equals 3? So now we actually need to plug in 3 into this and find out what that will approximately be equal to. 27. G of 3 is equal to negative 3 plus 12, 11, 10, 9. 9 divided by 3 is 3. 3 to the third power, we get 27 plus 27, which is 54 degrees Celsius. Okay, so there it is. That is the internal temperature of the potato at time t equals 3 is 54 degrees Celsius based on this model. And that's part C, and that's 5 points, right? So there it is. All right, anyhows, let's just go ahead and complete part B, which is take the second derivative. Well, dH over dt, distribute the negative 1/4, we get negative 1/4 h minus plus 27 over 4. Taking our second derivative, this is with respect to t, there's no t, so this is negative 1/4 dH over dt. The derivative of h is dH over dt. Derivative of 27 over 4 gone. It's just a number. We already know dH over dt is given to us by this. So this becomes negative 1/4 times negative 1/4 h minus 27, which is going to become positive 1 over 16 h minus 27. Very good. So there it is. We got a point for taking the derivative there, but now it wants us to figure out whether our answer in part A is an underestimate or an overestimate of the internal temperature. Well. What do we do here? What numbers can we plug in for H? That's what I'm interested in, because right now our second derivative tells us whether we're concave up or concave down. And according to this problem, it says the internal temperature of the potato is greater than 27 degrees Celsius at all times, at t greater than 0. So at all times greater than 0, we have to be greater than 27 degrees Celsius. Well, if you plug in any numbers into here that's greater than 27, are you concave up or concave down? Well, try it, right? You do 29 minus 28, that's a positive. 30 minus 28, that's a positive. So now we know d2, our second derivative of h is always positive, which is concave up. Therefore, at t equals 3, the internal temperature is an under approximation, right? Should make sense because we're going to be under approximating the curve. It's going to be an under approximation because it's concave down. And if you plug in 3, well, it was right up above, right? When we plug in a number at t equals 3, we know the temperature is greater than 27. That will be concave up. Therefore, we know that the answer in part A, the internal temperature is an under approximation from part A, right, which is the problem up above here. We know it was it said that the internal temperature is a 43 degrees Celsius. It's concave up. We therefore know this was a tangent line approximation. If you grab a tangent line, and let's say right here, right, it's concave up, right? This is some function that's, let me just draw that. There it is. If we draw our line tangent to this, it's going to be an under approximation, because our under approximation at 3 would be maybe here, and you'll see it's less than the curve, right? It's not going to be over, and that's why it's going to be an under approximation, very similar to the one we did previously. All right, that's roughly just about 15 minutes, which is going through over everything. You see how fast we have to go. just to try to make do with what we got. All right, my friends, you take care. Have a rest